Okay, so vectors in further maths kind of sits within the same idea of linear algebra with matrices, because we know that a vector is a particular type of matrix. It's just a column. Yes, it's just a particular type of matrix that we've got, and vectors are just talking about, well, I guess they've just got one column that they have here, okay? So we're going to extend lots of the things that we've looked at in regular maths, but also extending some of the ideas of things that we've done with matrices. And it makes sense that I'm doing vectors with you rather than Miss Chalmers, because I've done all of matrices with you. So we'll have some of those similar kinds of ideas, although we won't be doing anything like multiplying them in that kind of sense that we've seen already, okay? So the things that we're going to be looking at here, and actually I suppose before any of this, the first thing we're going to do is think about things in 3 dimensions, because in year 12 at the moment, everything in vectors we've done is in 2 dimensions. Year 13, all we do is make it into 3D. So we're basically going to learn year 13 vectors in about 5 minutes, and like a gap of 5 minutes. Then we're going to start describing things like equations of straight lines in 3 dimensions. This becomes really, really useful. Although you can describe lines in 3D with x, y, and z, it actually becomes quite a lot more complicated to do it in Cartesian form. I think you might have remembered Cartesian meaning to do with x and y. So we're going to use vectors to describe things in 3D, and you can already begin to think of what real-life applications that might have, because, surprise, the world is 3D, not 2D. We're going to look at equations of planes. Now, we've already looked at equations of planes before. Where did we come across equations of planes? Yeah, when we did stuff with matrices. What's an equation of plane in a Cartesian form? What does it look like? Do you remember what the standard form of it looked like? Think back to when we did intersections of, when we were talking about systems of equations. What did the equations look like? They said, oh, these are planes that you could do. Ax plus by plus cz equals d. So we already know the Cartesian form of a plane, but we're going to try and make that make more sense. And we're also going to come up with some vector equations of planes as well. The third thing that we're going to do is we're going to learn something called the scalar product, which is one of the ways of not necessarily multiplying 2 vectors. It's almost like a new operation that you can do with vectors about basically how you multiply them, but it's not in the way you would expect. And we're going to start finding out things to do with angles between all of these different things you can imagine in 3D, which is actually going to be a really useful thing if it's any real-world stuff. We do more stuff about equations of planes. We find out how things intersect with each other, and we find shortest distances. So everything we're going to be doing here is imagining a 3D world and how we can solve puzzles in that kind of 3-dimensional world. So before we do that, we need to think about some of the basic things to do with vectors. Now, I think we've already come across this before, but we know that things in the x direction, we use I. Thing in the y direction, we use j. And now, because we're going to turn it into 3 dimensions, we're also going to have k as well. Okay, so instead of now having vectors that just look like 3, 2, we're going to have vectors that could be 3, 5, -7, which represents things in 3 dimensions. So the journey would now be 3 in the x direction, 5 in the y direction, and 7 down in the z direction. Nothing super difficult there. We're just going to be referring to I, j, and k. It's probably worth noting, though, that x, y, and z, what could you say about the angle between the x-axis and the y-axis, the x-axis and the z-axis, and the y-axis and the z-axis? They're all perpendicular. They're all 90 degrees to each other. And that's actually why we've only got these 3 dimensions. We can't have a 4th dimension because there's nothing left. There's only those 3 ways you can make things perpendicular to each other. So one of the things we would be doing in year 13, but we're going to talk about now, is how we find the distances from the origin to particular points. So in other words, what does the Pythagorizing that we did in year 12 vectors, what does that look like when we change this into 3 dimensions? So let's have a look. I want to find the distance from the origin to the point P, which is 4, 2, 5. So let's presume that this is the x-axis, this is the y-axis, and this is the z-axis. The axes are sometimes written in a different way. Sometimes you may see that this is x, but then this is y, and this is z. It's just different angles. It's depending on how you think of it. Sometimes people think of this is like a table, and the xy plane is like the piece of paper on the table. Sometimes people think about this as X and this is Y, and they think about the board as being like the piece of paper with the other axis. So it just depends. You have to read whatever the context looks like in the question. So this is telling me that the point P is 4 along here, then 2 back in the Y direction, and then 5 up in the Z direction. So it looks like it's going to be something that's kind of set backwards all the way over here. Now you have to try and imagine that in 3 dimensions, okay? It's not actually on the board, it's kind of set backwards into the board, and it's set on top of that little point there. So there's a kind of 3-dimensional triangle that's happening, right? Now, if I wanted to find the distance from the origin to the point P, what other things might I need to find out first?
The modulus of the x, y.
Yeah, I need to find the modulus, the length of this xy section that we've got here. So if I just call this, I don't know, if I call this section A, and if I call this section B, then that part of the triangle would be C. So what is A actually equal to on this triangle? It's a right angled triangle here. And it's also a right angled triangle here. Root 20. I'm actually just going to write it out in full. I'm just going to say that A is equal to the square root of 4 squared plus 2 squared. And you're going to see why I actually leave it in this particular way. And B is equal to, what's B equal to? 5. So C, which is the hypotenuse of the triangle, C is equal to C squared equals A squared plus B squared. So C is the square root of A squared. Well, what's A squared? 4 squared plus 2 squared. And B squared is just 5 squared. So C is the square root of 45, root 45. But does that show us what the shortcut should be of how we find the distance from a point to the origin? Yeah, these 3 things that we've got here, 4, 2, and 5, to find the distance, you just do 4 squared plus 2 squared plus 5 squared. Luckily, Pythagoras in 3D isn't about cubing and cube rooting or anything weird like that. You can literally just square, 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 add, and square roots, okay? So to find the distance to the origin, of x, y, z, the distance is the square root of x squared plus y squared plus z squared. Nice and easy. And you may have looked at this at GCSE. You may have looked at 3D Pythagoras. And if you did do 3D Pythagoras, you may have done it slowly. You may have actually found out that distance and then done Pythagoras. But you could have done it all at once if only your teachers had just told you, oh, you just square all 3 of them, add them and square root them. That's the shortcut. Yes?
Would 3D Pythagoras be find the longest diagonal?
So 3D Pythagoras we're talking about in this context is finding the diagonal from the origin to the particular point that you've got. And it's not going to be much to change it if it's between 2 points. Basically, just to find the length of anything in 3D, you square them all, add them, and square root them, okay? So let's just have a quick think about how this then behaves in 3 dimensions. It behaves exactly the same as what things look like in 2 dimensions, but we just have added in that new idea. So to find the distance AB, the first thing I need to do is find the vector AB, which is just b minus a, which is just 105 minus 3, 6, minus 2, which is just minus 2, minus 6, 7. Yeah. Oh. Then just bring the other back in as a spare one, yeah? I knew I shouldn't have given them out last lesson.
I took it out and I did it.
Good job I printed spare ones, yeah? Exactly. So this is exactly how you do it in normal maths. You just subtract them to find them. And now, because we want to find out what AB is, AB, that's really messy. We know that AB is the modulus of the vector that we've just found out, which is just 2 squared plus 6 squared plus 7 squared. Anyone noticed why I've written it in a slightly different way to how, I don't know if Miss Chalmers has had you do it in a different way.
Because it doesn't matter if you square negatives.
Yeah, it doesn't matter if you square negatives or not, so I never bother writing in the negatives just because I think it's simpler not to. So you get root 89. So the distance between A and B is root 89. Now this is really useful because in real life, coordinates, if you're talking about things, actually are three-dimensional, the coordinates. So if you want to find the distance between 2 points, you can now see we've got this very simple thing of subtracting the coordinates and Pythagorizing. Very simple algorithms that can be done there. And I've wanted to do a reminder of to find the unit vector in the direction AB. Should be in the direction AB like this, but I can't print those arrows, so every now and then I might ask you to add them on. Does anybody remember what a unit vector is and how you find a unit vector?
Is it a vector with a modulus of 1?
It's a vector with a modulus of 1, and we normally say a unit vector. Do you remember what the notation is for a unit vector? Yeah, it's called a circumflex, or a little hat that goes on top of it. And how do you find a unit vector?
When you divide it by
Magnitude.
something.
You divide it by its magnitude. Okay? Because imagine you had a vector, like a 3, 4 vector, like 3, 4. Its magnitude is 5. But I don't want it to have a magnitude of 5. I want it to have a magnitude of 1. So if I divide them both by 5, unfortunately, 4 divided by 5 is not 3 over 5. If you divide them both by 5, it's still going the same direction. Why is it still going in the same direction? Because it's still a multiple of it. It's a fifth, so it's still a multiple. But if you square this, and add this, you would get 1. And unit vectors, at the moment, I'm just telling you, they're useful. But unit vectors are useful, okay? I'm not going to tell you why, just because I have to go too deep to tell you why they're useful. So for this one that we've got here, the unit vector in the direction AB, well, we could just say that it would be, this is the direction AB, -2, -6, 7. And it would just be all divided by root 89. I'm happy to leave it like that because I don't think that going inside the vector is going to make it look any nicer. So I'm just dividing it by root 89 to make it have a length of 1. Again, nothing new. I'm just trying to connect this together with what we've done in year 12 vectors so far. The gist of it is anything we've done in 2 dimensions, you can do it in 3 dimensions, literally any of the stuff in year 12. So when we get to those year 13 lessons, that'll be in November next year, I'll probably get you guys to do further maths practice rather than actually learning the year 13 vectors. That's probably how I've been doing it with these guys this year, okay? Can I go on to the next bit? So this is where things get interesting, okay? You might want to, there's some animations for it rather than you having a look at the page there. So we're going to have a look at how we consider the vector equation, the equation of a straight line in 2 dimensions to then think about what this might look like in 3 dimensions. So we're going to consider this particular equation. We're going to consider y equals 3x plus 2. So I've said that x is obviously a variable because that it can vary. And we consider different values of x, and that gives us different points on the line. So when x is 0, we obviously get a y value. When x is 1, you get another point. When x is 2, you get another point. I know I'm stating the obvious here, but you're going to see how it all then connects together. And then what we do is we just go oh, well, actually, I know that when x is 0.5, it's in here. And I know that when x is 0.1, it's in here. And we just infinitely say, well, I'm not going to do all of those points. I just know it's going to lie all along that line that we've got. So in this bit here, I've said it's worth noting that in y equals mx plus c, whilst x and y are variables, m and c are constants. After these are set for a particular line, they don't change. And we're going to see how this compares with things for vectors. So I've said, can we do something similar with vectors? And we're going to consider this particular equation that we've got here. And R is referring to a position on a line. Just like here, it was a combination of these things that referred to a position. This is referring to the position on the line. What happens as we vary lambda? Well, if we have some axes here, this is where it starts off, the origin. This is not where the line starts off. This is the origin. And the first thing that we do is we have 3, 0, 2, which is going in some particular direction that we've got here. And that's when lambda is equal to 0. Because when lambda equals 0, the point on the line is just 3, 0, 2. But when I change lambda, maybe when I add 1 to lambda, I then get that lambda becomes 4, 1, minus 2. Can you see how I've just, if this is just 1 here, I get the 4, the 1, and the minus 2. If I add on another lambda here, it's going to move in that same direction because we're adding on another of those vectors, which means it must be moving in that same direction. So when lambda equals 2, you get 5, 2, minus 2. So all you need to keep doing is varying the value of lambda, which we call a parameter, and it will sketch out a line, okay? Even if you go backwards, this is a mistake here. This shouldn't say 5 here. This should say 2. And I think it should say 2 minus 1 minus 2. I forgot to change that. So if you could change that to a 2 and that to a minus 1, and that should be a minus 2. And you may like to add that this O here is the origin. If you know that O is origin, then it's the origin. So, actually, before I talk about this bit, like we've got here, right? We said that x was 1 and that x was 2. In between, you can have that x was 1.5. It's the same thing. If I wanted to say, like, actually, somewhere in between here would be minus, lambda was minus 0.5. And actually, if I wanted to go way off into the board in that direction, lambda would be like 1,000. So it allows us to vary and travel along this line. So what do we think the role, without looking on your pages, what do we think the 3, 0, minus 2 tells us? And I don't want it to do with stuff up here. How would you describe what the 3, 0, minus 2 does, or what it is? Yeah, it's the starting position. When lambda is 0, it is the position that is on the line. 3, 0, 2 is a position that is on the line. And what do we think 1, 1, 0 represents? It's the change in the coordinates as we move along here. Sorry?
Because it's 0 for Z, Z doesn't change.
Because it's 0 for Z, Z isn't changing. So it just changes in this thing. But I want to try and give this a name about the way that this thing is moving each time we go along here. This is 1, 1, 0, 1, 1, 0, 1, 1, 0. It's a direction. It's a direction of how this particular line is moving. What you said about is how the coordinates are changing. How the coordinates are changing is the direction that we've got there, okay? So the role of this is it's a position vector of some arbitrary point on the line. This could have been 3, 0, 2, or actually I could have started it at 4, 1, minus 2. I could have started it at 5, 2, minus 2, or I could have started it at this correct one that should have been 2, minus 1, minus 2. As long as the first bit that you've got written here is on the line, and this is a vector that is parallel to the line, if this is a direction vector, then you have come up with an equation that is of the line. So the 1, 1, 0 is the direction of the line. Now, this equation for the Cartesian is pretty unique. If you make y the subject, it pretty much has to look like that. The only thing is, I guess you could write y equals 2 plus 3x. But this equation, can you try and tell me why this is not unique? There's a few reasons why it doesn't have to be unique for this particular line that I've got here. There's a few things we could change about it, and yet it would still represent the same line. Sam?
The direction could be like any multiple of what it is.
Absolutely. The direction could be 2, 2, 0. It could be pi, pi, 0. It could be minus 350, minus 350, 0. If you changed the scale of this direction vector, but you still wanted to land at, I don't know, this point that was lambda equals 2, what would change about lambda would have to change, right? Lambda would have to be a different value. So this lambda is the thing that we control, and we say, oh, I'm going to change lambda to get to whatever point I want to get to. What else makes this line not unique? The position vector. Yeah, it doesn't have to say 3, 0, 2 here. It could have said 5, 2, minus 2. Or it could have even said 103, 100, minus 2, because that would also be on the line. So there is not a unique way of writing a vector equation of the line. What were you going to say to me?
What if you like change the value of z? Would that not be a straight line?
If you changed this thing that you had here, it would still be a straight line, but it would just not be this straight line. Although this straight line looks like it's in 2 dimensions because it's on the board, it would just, if you change if you're changing this to something else, it will no longer be traveling in, say, like this direction. It may then just go traveling in a slightly different direction. So it's no longer the same line. It still describes a line, but just not that line. It doesn't have to be, by the way, 1, 1, 0. It could be like 5, 2, minus 3. It could be any numbers at all, as long as those bits are describing the direction of the line that we've got, okay? So let's think about how these kind of things might behave. So I've written here that's kind of the boxes of the stuff we need to know. The vector equation R of a straight line is R equals A plus lambda B. Notice how when it's typed, this is bold, and this is bold. If it was written, these would be the bits that are underlined. Why is lambda not in bold or not underlined? It's a, what, sorry? Yeah, and actually lambda's got a special name in this case. We don't necessarily call this a variable. We're actually going to call lambda a parameter. And we pick whatever value of lambda is necessary to get to a particular value on the line. So the left-hand side, the R, and we always use the letter R, gives you a coordinate or a position from the origin to a particular point on the line. So some important understanding points. A and B are constants, so it's fixed for a given line. So that would be like the position, and that would be the direction, whilst lambda is a variable because it varies, but the way we actually call it is we call it a parameter. It's often very helpful to write this as a single position vector. So that previous one that we had, that was R equals this, we are more familiar to see this as R equals 3 plus lambda, lambda minus 2. Hang on, let me just change that. This is not more familiar with what you will see. This is more familiar with what you will use. You will often see it written like this in the question and the problem, but you will probably find it more useful to combine them into 2 things. And you can see how they've been combined. They've just multiplied this by lambda, multiplied this by lambda. There's no lambda in the bottom bit because of that. Okay, so you can start to really clearly see how the coordinates are of that line. And I've said here that it's highly important you can distinguish between the position vector R of a point on the line and the direction B of the line. So this whole thing doesn't explicitly tell you what the direction is. You have to look at this part of it that tells you the direction it's traveling in. And that's because the first bit doesn't tell you the direction it's traveling in, it gets you onto the line. The second bit tells you how it's traveling. And that's the interesting thing. We want to know how this line is traveling. So we're going to start putting these into just a few examples. And it's pretty straightforward. I think it's straightforward if we get our head around this idea. If we're not sure of this idea, we can always speak about it a little bit more later on as well. So here, the equation of line L1 is R equals 3, 0, minus 2 plus lambda 1, 1, 0, the one we've already seen. Find the vector equation of a line parallel to L1, which passes through the point 2, 5, 1. So if it's parallel to it, it's still going to have the 1, 1, 0. Equally, we could have written 10, 10, 0, or minus 5, minus 5. We could be annoying if we wanted to. And I'm actually going to put here instead, I'm going to use mu rather than lambda, because I'm talking about a different line. So I think it makes sense to talk about a different parameter so I don't get confused with them. And then the thing that I want written at the beginning is it's going through the point 2, 5, 1. So that's it. That's how we construct that line. And you'll have to look at these directions and interpret whether things are parallel to each other or not. So you need to be in the habit of looking at two lines and seeing their directions. With y equals mx plus c, it's so easy, isn't it? This is a little bit different. You've just got to get into a new habit of this. This one says, find a vector equation of the straight line which passes through the point A with this position vector and is parallel to this position vector. So, Arifa, what do we think the whole thing should look like then? So it's passing through this point and it's parallel to this point, this vector, not this point.
So it'd be something plus mu 7 minus 3, 0.
7, 0, minus 3, just because of the I, J, K, there's no J here. And what do we think this bit here is going to be?
It's going to be 3 minus 5, 4.
It's just 3 minus 5, 4, because this is the point that it goes through, and this is the direction that it's going in. Because if it's parallel to this, then it must have that as its direction. And I'm just going to put these together just because we want to get into starting to do this. Even though this is the way you would want to leave the question, what would this look like as a single combined vector? 3 plus 7 lambda and 4 minus 3 lambda. And if you were presented with something like this, I'm hoping you would be capable of pulling it apart into these two things as well, if you needed to. This one's a bit different. And Sam, I want you to think about how this one is different and help me answer this. It says, find a vector equation of the straight line which passes through the points A and B with coordinates 4, 5, minus 1 and 6, 3, 2 respectively.
I guess you'd find the direction by like subtracting the two vectors.
Great.
A, B, that would be the direction. And
Okay.
you just take one of the points as the position.
Good, so this time they haven't told us what direction it's going in, but we know 2 points on the line, so if we subtract them, we will know the direction of the line. So I'm just in the habit of doing AB, which is going to be 6, 3, 2, minus 4, 5, minus 1. Let's squeeze it in here. 6 minus 4 is 2, 3 minus 5 is minus 2, 2 minus minus 1 is 3. So you've got 2 minus 2, 3. So that's going to be the direction. And my position vector, which one do you want to put in, A or B? A. So let's just do 4, 5, minus 1, plus lambda, 2, minus 2, 3. That's it.
Does it matter which one you put in?
No, absolutely not, because there is no unique line. There is no unique vector equation of the line. If you ever see a mark scheme for this, where you have to come up with a line, particularly if it's like when there's a lot of information, they will say, except this, except this, except this, except, and there's like loads of different things that are possible answers. But you don't need to get bogged down by that. You can just be like, as long as I've got a point on the line and a direction. A little tip though, if this here is ever something like, I don't know, 200 minus 200, 300, I would simplify it and just do 2 minus 2, 3. Because it just means your numbers are going to be smaller to deal with. So if you ever got something like this, you should simplify. You can't simplify though. If this was 400, 500, minus 100, that's a position. You can't simplify a position vector because parallel position vectors are not the same position. If they're, multiple positions are not the same thing. But if these were multiples, then you can simplify them. So you cannot simplify it if it's a position vector, but you can simplify it if it's a direction vector. So I'm not telling you, if you find that confusing, just don't simplify it. But for direction vectors, it often can be helpful to simplify them. So I will, at some point, that will come up and I'll probably just do it and you'll be like, oh, cool.
Would you not write that last bit as a one vector?
And then you could write that as, if they asked you to come up with the equation of the line, this is the thing the examiner would look for.
Standard equation.
This is the standard version of it. If I, at some point, when we start doing shortest distances and angles and things, you'll combine them. So if it asks for the equation, leave it there. But just so you know, we're often going to push them together because the maths just becomes a lot easier when you push them together. So we're going to go a quick here. I know there's a lot of me explaining things, but hopefully it's all making lots of sense. So this equation is written in this way. And here's going to be an instance where it might be better to show them combined together. So we've been given the equation of a line, and it tells us that AB0 is on the line, and we want to find out the value of A and the value of B. So R is 3, 2, minus 5, plus this time it's T rather than lambda, 1, minus 6, minus 2. And now I'm going to put them together. So you get 3 plus t, 2 minus 6t, and minus 5 minus 2t. Now because AB0 is on the line, AB0 has to be equal to 3 plus t, 2 minus 6t, minus 5 minus 2t, because it's on the line. Which is best to look at, I, J, or K? K. So we look at the K component. And from our K component, we get 0 equals minus 5 minus 2t. So t is minus 5 over 2.
Now you do put that into 3 plus t.
Absolutely. So now we can say that A is equal to 3 plus t, which is just 3 minus 5 over 2, which is a half. And B is equal to 2 minus 6t, which is 2 minus 6 times minus 5 over 2, which is negative and a negative though.
Is that 17?
17. Because minus 6 times minus 5 over 2 is 15. Yeah? So you've got to find out what this t value is because it helps you find out the other ones. And you don't need to draw a diagram here, but to think about it, here's the origin. 3 to minus 5 gets you onto the line. So let's call this 3 to minus 5. The direction of the line is 1 minus 6 minus 2. And that is here when t is equal to 0. Now our value of t was minus 5 over 2. So probably going to be somewhere over here. T equals minus 5 over 2. So what we've actually just got here, the AB0 is the vector that takes you from here to here. This is your AB0. It's actually, because it's a position vector, right? So you don't need this diagram. This doesn't help us solve the problem, but it's kind of nice just to look back on it and to think to yourself, oh, well, if that's t is 0, if I had to draw a diagram, this is what it would look like. Because in the future, diagrams become very important to us in this, okay? And obviously, this is the origin. This is O. As much as we would like to, we can only draw 2D diagrams. So we just make everything flat, even though we know this is happening in 3D space. Okay. The next question has given us 2 vector equation lines. It's given us r equals blah, blah, blah with a lambda and r equals blah, blah, blah with a mu. And we need to show that they are the same as each other. If they are the same as each other, what can you tell me about the 2 lines if they're the same as each other?
The direction is going to be more clear.
Okay, so if the same, the directions must be parallel or multiples. If they are also the same, what can you tell me about these bits?
To line both lines.
Yeah, this point here also has to be on that point there. If the same, the a vector of the second equation must also be on the first equation's line. That's the thinking that goes on behind this one. If the directions are the same, and if this point also is on this point, on this line, then they must be the same line. So first of all, let's deal with number 1 here. How can I show that they are parallel?
Do you see that the second bit is a multiple?
Yeah, what's the multiple? 2. So I can say 6 minus 2, 4 is 2 lots of 3 minus 1, 2. So they are the same direction. How do you think I can show that this is on this?
With the value of lambda.
Find, what does that say?
Value of lambda.
Find a value of lambda that,
That would make that first equation equal this part A.
good. Now, you may be able to just spot this because they've already told us they're the same, okay? Can anybody see what is the value of lambda that makes the top one this position?
1.
1. Good. If you just look at the first bit, if we want the I component to be 8, we've got 2 plus 6 lambdas, so lambda has to be 1. So when lambda equals 1, R equals 8, 3, 1. So 8, 3, 1 is on the line. Hence, R equals 8, 3, 1 plus mu 3 minus 1, 2 is the same line. If it wasn't the same line, you would have to show that the directions were not multiples of each other, and you would have to show that there is no value of lambda that makes it true. So you might find it that makes it work for the I component, it makes it work for the j component, but you just have to show it doesn't work for the k
The
component.
direction is multiple. That means they're parallel, but just prove that they're on the same line. That's fine.
Yes, excellent point. If they had the same direction, but this point here didn't lie on it, we would have 2 lines that look like this, that were parallel. But the 2 lines we've actually got are that line and that line. We've literally got the same line twice. And it's me just illustrating the point that vector lines can be written in many, many, many different ways. Then kind of weird compared to our other ones. We've got so used to there being like a unique answer. There's one more thing, isn't there? An example problem. We'll do a final example problem, and then it's going to be a big chunk of practice for you guys. Do you want me to go back to that previous page, guys? Yeah? You can start doing the next problem if you want. What does it say?
Distance of 3.
Yeah, that one we'll do together. That one's a bit trickier.
Doesn't mean that lambda equals 3.
No.
No. Because lambda is multiple.
Oh, the distance here is not the modulus.
Yeah.
Oh,
Well, work that.
So have a think about that. That's where it gets a bit harder. Ready?
Yeah.
Okay.
There could be like more than one answer.
Yeah.
Because it could be.
Because it says find the coordinates of the points. So here we've got the equation of a line, And we want to find the coordinates of the points on L1, which are a distance of 3 away from 3, 4, 4. Now, there's a few different ways of thinking about this question, right? I think I might draw a diagram, and then I think afterwards we might do it in like an algebraic kind of way. So imagine we've got a line, and we've got a point, which is 3, 4, 4. And I want to find the 2 points, well, I think there's going to be 2 points on the line that are a distance of 3 away from it. Why do you think I've said 2 points? What could the lines look like? Show me with your hands what they might be. Yeah, there's going to be like one of them could go here, and one of them could go here, and they're going to be the same distance. They're both going to be a distance of 3. Now, we know that any coordinate on this line could be here, could be here, could be here. Any of those coordinates on the line is r. And r, if we combine these together, what does it combine as? Minus 1 plus lambda, lambda, and 3. So any of these coordinates, a general coordinate, here, or here, or here, is minus 1 plus lambda, lambda, 3. Could be anywhere at all. That represents a general coordinate. That's a really important point. Now, if I want to find the distance between these 2 points, let's just ignore that it's got lambda in it. How do you find the distance between 2 points? What's the method? But before you do the modulus, you've got to do something, haven't you? You subtract them, and then you can find the vector of the thing between them, and then you can do the magnitude. So what we're going to do is we will subtract the vectors, and then we will Pythagorize and make it equal to 3. And that should tell us the 2 points that we've got. So I'll subtract them. It doesn't matter which way round you subtract them. Probably going to be easier to do that one, take away that one. So when I subtract them, I have minus 1 plus lambda, lambda and 3. And I'm going to subtract 3, subtract 4, and subtract 4. And so I get minus 4 plus lambda, lambda minus 4, and minus 1. So what that actually is describing now is any of these vectors that I'm indicating on the board. Yeah? It's indicating how do you go from that point to that point, or vice versa. It depended which way round we subtracted them. So now I'm going to Pythagorize this. You can Pythagorize this. So you've got minus 4 plus lambda, which is the same as lambda minus 4 squared. You've then got another lambda minus 4 squared, and you have a plus 1 squared, and that's equal to 3. Simple, it's just a quadratic. Any suggested steps that are sensible here?
Square it.
Yeah, square it and get rid of that root symbol. So we know it's going to be equal to 9, and let's just start expanding those brackets. So a lambda minus 4 squared is a lambda squared minus 8 lambda plus 16. And then we've got another lambda squared plus 8 lambda plus 16 plus 1. I've done that a little bit.
Minus lambda.
Yes, yes, yes. I was going to say that was weird that they cancelled out. Thank you. Minus 8 lambda plus 16 plus 1. So our equation is lambda squared minus 16 lambda plus 33 minus 9, which is...
Should be 2 lambda. 2 lambda squared.
Thank you. Gosh, it's not a good day for me, is it? So you get 2 lambda squared minus 16 lambda plus 24. You can do it on your calculator. I'm just going to do it old school.
Lambda minus 6 lambda minus 2.
I got 2 and 6.
No, I'm talking about the brackets.
Oh, good, good, good.
Why did you put it back in?
Yeah, and then we just put it back in. I forgot we hadn't even done that yet. So before we even do that stage, I just want to explore a couple of things about this line, okay? here is where lambda is equal to 2. Here is where lambda is equal to 6. What do you think this point is, where these are equal distance? What do you think the value of lambda is here? Good. Lambda is 4 in that particular bit there. What do you think is true about this point and this line? What could you tell me about this red distance? Maximum?
The longest.
Longest? This is clearly longer than that. What do you mean? What do you say? Shortest distance. How could you go from saying it's the longest distance to the shortest distance? It is. It's the shortest distance. And so we've already learned about something we're going to be learning about much, much later on, about shortest distances. The shortest distance is when it's perpendicular. So we've done something extra there. The shortest distance is when lambda is 4. You can use this idea of the kind of, every time you do a lambda, you move the same distance along the line. It's not random. It's sort of spaced out with it. So Haroon's final thing that he said we should do is substitute lambda in. Now it's probably easier to just substitute it into this thing that we've got up here. So we can just say, well, the two coordinates would be -1 plus lambda, which is going to be 1, lambda, which is 2 and 3. So we've got 1, 2, 3. And the other place is -1 plus 6, which is 5, 6, and 3. So these are the two coordinates that have a distance of 3 away from that point. This is a much harder problem. Any questions about this? What were you saying there, Locke?
Wait, does the first one, 1, 2, 3, have a distance away from 3 though?
This one, if you did this and this point, if you subtract them and Pythagorise them, you should get 3. So I'm just going to test it out. Why don't we test it? So if I do this one, take away this one, I would get -2, -2, -1. When I did 1 take away 3, 2 take away 4, and 3 take away 4. And when I Pythagorise that, I would get 2 squared, 2 squared, and 1, which is 4, 4, and 1. So I get √9, which is 3. If I do this one, again, take away 3, 4, 4, I would get take away 3, take away 4, take away 4. I get 2, 2, 1. And when I Pythagorise that, it's clearly going to be the same thing and also give me a distance of 3. Those are the only 2 points, and the only 2 points, obviously, can be from that diagram. There is a scenario, though, where there could only be 1 point. When would there be only 1 point, do you think? When 3 is the shortest distance, it would only be 1 point. Okay, you can imagine it just being, if that was 3, you could only have one of those there. So I've got a long list of questions from this exercise. I think we'll probably do it for about 25 minutes, and then I'll try and do like a little bit just to finish up on this topic as well. I know you've listened really carefully then, so well done.